Throughout the course so far, we have seen that the concept of mapping a function over a data structure is actually more general than that it just applies to lists. So of course we have our map function on lists, which I'm going to present to you once more, and I'm explicitly going to call it map list. As we know, we can write it like this. It takes a function from A to B, and then it takes a list of A's and turns it into a list of B's. And we have two cases, one for the empty list, and where we don't actually need the function, and one for the cons case. And the concept of map is always that it produces a structure of the same shape. So for the empty list case, we produce an empty list again, and then the cons case, we produce a cons again, right? And then what are the components of the list that we are producing? Well, we are applying the function to every element, so in particular to the first element of the list, and then we're applying map list recursively to the rest of the list. We have seen a similar function for the maybe type. I said that it's a useful function to be able to take the result of a potentially failing computation and apply a function to that result, but to propagate the failure in the sense that if the result of the original computation was nothing, then the overall result should be nothing again. But if the result of the original computation was just, then we should be able to get access to the result and do something with it. And that's exactly what map_maybe does. So it takes a function from A to B again, but now rather than taking a list of A to list of B's, it takes a maybe of A to a maybe of B's. Okay. And again, we have two cases, and again we have one for nothing where we don't actually need the function, and we have one for just. And again, we have this principle that mapping produces something of the same shape. So in the nothing case, we produce a nothing again. In the just case, we produce a just again. And what is it that we are producing in the just? Well, the just contains the element of the maybe structure, and therefore we are going to just apply f to x. We've also seen tree data types, such as this one, where we say a tree is a leaf of an A, or it's a node of two subtrees. So this is giving us binary trees where the leaves can contain elements, nothing else can. And again, this is a container-like structure, and again, we can define a map-like function for it. We can define map tree, taking a function from A to B, but this time going from a tree of A's to a tree of B's. And in this case, we do need the function in both cases, so we either have a leaf of X, or we have a node of a left and a right subtree. Again, this mapping function follows the principle that it creates a tree of the same shape. So in the leaf case, we produce a leaf, and in the node case, we produce a node. Now, in the leaf case, we have an element, therefore we have to apply our function f to the element. In the node case, we have two subtrees, and therefore we have to recurse twice. So we call map tree with the same function f on the left subtree, and we call map tree with the same function f on the right subtree. So we've now seen three different data types that support the same function. So that seems to suggest that mapping over a data structure is also a common interface, that it's worth sharing, that it's worth giving a common name to, namely mapping, that of mapping, and to have a type class, perhaps, that covers this. But what's slightly unusual is that so far we've had type classes that are implemented, where the interfaces are implemented by concrete types, such as integers, booleans, characters, doubles, right? Or even lists of integers, lists of booleans. Whereas here we have a concept that inherently applies to parameterized data types, sometimes called type constructors, because we have to have a parameterized data type. Otherwise, it does not make sense. This is all about changing the element position or potentially affecting the element position of this data type. So this is not mapping is not applying to integers or booleans, it's applying to lists. It's also not applying to lists of integers specifically, but to lists in general, right? To lists as a container data structure that has an element type, and to maybes and to trees. And in that sense, it's ever so slightly different if we want to define a type class for this, which is called Functor in the base libraries or in the prelude. We are parameterizing the type class over a type f, but the type f itself is a type constructor, is a type that is parameterized by something. And then the method of the functor class we're calling fmap. And then this fmap method has exactly the shape that we are seeing here, only that where we have list and maybe and tree, we now use our f. And here f is applied to an argument, right? So that's the difference. The f is just a choice of a name that we choose f here because it suggests something like, functor is a name that is given in category theory to type constructors like this, to parameterize types like this, and the f suggests that name again. So that's why we choose that variable name. But the important thing is that it's a parameterized thing that we apply to A here and to B here. And that's very essential about the whole concept of mapping, that we have an argument position, that we have an element type, and that the function can affect these elements. And in order to get no name clash for the time being, I'm going to hide the predefined version in the way that we've seen before. Okay. And now I'm just going to give instances for functor. And now I have to refer to the list type without giving it an argument. Right? So I have to say I want to make lists an instance of the functor class so that I can have a list of A here and a list of B here. I cannot write list of A here because now I'm already applying the list type constructor to an argument. We have seen a number of times that Haskell actually allows us to use this notation here, this syntax for referring to lists on the type level without giving an argument. It looks like an empty list, but it is actually the list type constructor. So funnily enough, right, I can write 1, 2, 3 is of type list of integer. That is allowed in Haskell, but it also allows me to use the list type constructor in prefix notation if I really want to, and then it's written like that. And that is what we're doing here. We're making lists an instance of functor. And then let me enable instance signatures once again. The language extension that allows me to give an explicit type signature now here for fmap. Right, and literally speaking, I have to write this function here. Right? But that is just other syntax for writing list of A to list of B. Right? That is just a syntactic abbreviation that we can use. Rather than using the list type constructor in prefix form, we can use it in this more convenient and generally much more widely used mix-fix form where the brackets are surrounding the type variable name. And then we have to give our implementation, but we have already given an implementation. So rather than repeating it now, I'm just going to say fmap is equal to map list. Right? So I don't have to repeat the whole definition. And then I can make maybe an instance as well, where I now get the type signature maybe A to maybe B, And that is exactly the type signature of map maybe that we have already given. And finally, I can make tree an instance as well. And there I'm getting tree A to tree B, which is exactly the type signature of map tree that I've already given. Okay, and now if I load this, I can try this out, and I can use the same fmap for all these different structures. So I can fmap on lists, incrementing every element of a list. I can use fmap on maybe, incrementing the one element in a maybe, or if it's a nothing, returning nothing. And if I have a tree of integers, something like this one, I can increment the integers as well, only that I have not actually given a show instance for my trees, and therefore the result cannot be shown. So I should, in order to make this more pleasant, derive a show instance for it, and then I can do this as well. Okay, so, and this functor class exists in the prelude and in the Haskell prelude as well. So rather than defining my own functor class, I could actually use the predefined one. So what I could do is I could not hide the original definition again. Now I'm getting error messages on these because now there's ambiguity between which functor class I mean, whether I mean my own that I've defined here or the one from the prelude. So I can, if I don't want to delete it, I can just rename the function here. Now you can see once I rename my class, I still get error messages for the list instance and the maybe instance, and that is because these already exist. Right? We already have an instance declaration. We get an error message that says duplicate instance declarations, and that is perfectly fine. We cannot make the same data type an instance of the same type class twice. But for tree we don't, because tree is a data type that I defined in this module. And for tree we can actually give the definition just as I did, so it just works as the instance for the prelude-based functor class. And for the other two, I'll just change this to my fmap, so keep it working. But this is actually an example of us making trees an instance of the functor class, of the actual prelude functor class. And still I can do this for all three types, because the other types are already an instance of the functor class, and they also support the built-in functor class. Right? And fmap can be used just as map. So Haskell, for historical reasons, does actually support map and fmap, map being the map function specific to list, and fmap being the generalized map function that works over other types as well. If you are working with a list, it is your choice whether you want to use one or the other. It amounts to the same. Let's do an info of the functor class as well. And we can see that it actually has one more method, but there is a default definition for that one, so it is perfectly fine to just provide a definition of fmap. And what this operator here does is it just ignores the elements that are in the original structure and replaces all the elements in the original structure with this one. And it's basically mapping a constant function over the original data type. That's the default implementation of it. So if we map a function over here that ignores its argument and just always returns the same element, then we get exactly the behavior of this operator. So let's give an example for this. If I use the number 3 and I map this with this constant mapping function over the list of 1 to 10, I'll just get a list that contains 10 copies of the number 3. Or if I take the character x, it doesn't have to have the same type as the original structure, right? And I map that with this constant mapping function over a tree that contains the numbers 3 and 8. And the 2 leaves, then I get a tree of the same shape, but just both elements have been replaced with x. There also is an operator that is written with both angle brackets, this one, which is just a synonym and a symbolic operator synonym for the fmap function. It has exactly the same type as fmap. And it is exactly the same as fmap. So it is your choice whether you want to write fmap or use this operator. Again, this is just whatever you prefer. You can use the default, the prefix version, or the infix version. Sometimes one is more convenient, sometimes the other. Both are in use, so it is useful to know the presence of this infix operator. Now, we can look at the instances that are defined for the functor class. So there is this instance for tree, which we have just defined, but the others are all coming from the standard libraries. And so maybe and list are the ones that we've discussed. IO is one that we'll discuss in the remainder of the course. And there are a few more instances that are defined here. There is actually one for functions. I can briefly look at that in a moment. And there are somewhat, I would say, somewhat controversial ones for either and pairs, which also look a little bit strange. And they're even more controversial, I think, in the context of the foldable class, which I'm going to discuss next. But let's briefly look at them in the context of the functor class, and let's see, perhaps in the context of our own functor class. If I wanted to go back to my own functor class and just make the either type an instance of functor. So remember that either is a type that has 2 type parameters, a and b, and we have a choice between, left, sorry. We have a choice between applying a constructor called left and applying that to an argument of type a, or a constructor called right and applying that to an argument type b. I've given this definition as a comment because it already exists and I currently don't want to replace it. So, but if I say I'm going to apply this left constructor to a character and I want to see this as an either of a character and a boolean, then that's fine, right? And if I apply the right constructor to a boolean, then that is fine as well. Now, if you look at the functor class, the way we defined it and the way that Haskell defines it, it expects a data type with 1 parameter, but either has 2, and it has, in a way, 2 notions of elements, like the things that are in the left constructor and the things that are in the right constructor. But this doesn't fit. We would, if we wanted to support some form of functor-like class that works for types that have 2 arguments, we would have to define a different class. And in fact, there are there are other libraries in Haskell that define a type class called bifunctor, which is specific for data types that have 2 parameters, and you can give a separate function for affecting the one and for affecting the other argument. But if you want to make either an instance of the myfunctor class or the predefined functor class, you still can if you treat it asymmetrically. If you think of the first of the 2 parameters as being a constant thing and the second as being the element that you can map over. Right? Because if you partially apply either to one type argument, partial application on the type level, then it is like a type constructor that still has one more type argument. And that is the way this is done in Haskell. So there is an instance, functor, for either a. So we give one argument here, and then the second argument is the one that is supplied here in the type signature. And then our myFmap function has to be of type a to, oh well, actually I should now not choose a to b here because I've used a as the first argument. Perhaps let's just like make this more explicit, use a completely different name as the first argument of either. And then we get either xa to either xb. Okay, and how does this one work? We have two cases for left of an x, let's call it x, because if it's a left component, then it is an x, or right, and if it's a right component, then it's an a. And now, because we treat the two things differently, right, we cannot apply our function to the thing that is contained in the left component. We have to, I actually forgot to pick up the function, that's why this is all underlined. So we have to produce something of left again, but we can only produce the original x again, because we have to go from an either xa to an either xb. So if we are in the left component, we have to treat this as a constant thing. If we are in the right component, we can apply the function to our a in order to get a b, and we actually have to apply it there. So, and this leads to somewhat asymmetric behavior, right? So fmap of or my fmap of +1 of left x is going to be left x, whereas or even left 3, right? Even though, I mean, this is more confusing because now it looks like +1 could affect the 3, but it doesn't. But if I use it on right 3, it does. And the same happens with the predefined fmap instance, right? So it behaves in exactly the same way. Behaves asymmetrically. It treats the thing that is tagged with right as the actual element type of the either thing, the thing that is tagged with left as some piece of static information. This is a bit confusing, I think, and I think it would be better if the either constructor, which looks relatively symmetric, right? If it would be like if there was a different version of this either constructor, which by its naming suggests a less symmetric use, and that constructor had, or that type had, this instance. But often either is being used in this way, actually. Often either, one common use case of either is in the combination that you say either error message or some result type. So, and the result type is context dependent. Every kind of function can have a different kind of result. Some functions have an integer result, some functions have a Boolean result. You work with different functions and combine them, but within the context of a certain part of your application, you have a common error message type, and that never changes. So, and that is a situation in which this asymmetric instance of the functor class comes in useful, and that's one reason why it is there. Such an asymmetric instance also exists for pairs. If we look here again, we see that here. This is the pair constructor partially applied to its first argument. And there it's arguably even more confusing because, again, the left component of the pair is now treated statically. The right component of the pair is treated as the element. So it's like a piece of information that is stored in the right, information that is tagged with some extra static information. But it allows you to write confusing things like this, where you say, I want to do fmap of increment by 1 to the pair of two integers, 3 and 4. And the left component is left unchanged and the right component is incremented. But this is also because the left component could be of a different type. The type is not affected by this. The type of the fmap function on pairs is only changing the second component. Once again, if you wanted to be like more general, you would need for pairs, because pairs can have two different components, you would need to have a mapping function that can actually affect both components independently, that takes two functions, just as for either one to affect the left component and another function to affect the right component. And there is such a thing, as I said, it's called bimap. But independently of that, you can still make it an instance of the normal functor class by treating it asymmetrically, and that is what Haskell chooses to do. Let's move on to the foldable class. The foldable class is similar to the functor class in the sense that it also parameterizes over a type constructor. The foldable class is otherwise rather strange because it has very, very many methods. Right? And we see that it has quite a few familiar methods. It has fold R and fold L and fold L prime. Okay. And it has null, which checks whether something is empty. It has length, which computes the length. It has elem. It has things like maximum or minimum. It's the maximum and min function generalized to a container structure. It has things like sum and product. It has a minimal definition that allows you to get away with defining just a single function, either a function called fold map or a function called fold R. We see that the fold map function mentions a type class that we have not yet discussed, that is called monoid. I may make an optional video about monoid, but I'm not going to go into this here. For what we need to know right now is that conceptually, what foldable captures is a generalization of all sorts of container structures where the elements occur in an order. And if they occur in a particular order, then you should be able to extract them, all the elements, as a list. So in particular, the foldable class has this toList function. So actually, by the way, the fact that this is prefixed here, that these names are qualified and the others are not, that is coming from the fact that certain methods of the foldable class are available in the prelude, and other methods of the foldable class are only available via this data.foldable module. If I just import data.foldable either in my source file or here in GHCI, I do this again, and then these strange qualified names disappear because now all of these names are actually in scope. Okay. So the toList method says, like, this is a data structure that can be converted into a list, or the elements of this data structure can be extracted in a list. And then all the other methods are conceptually just defined via this toList method. So, right, if there are no elements in the list of elements that is being extracted, then the null function would say true, otherwise it would say false. The length function should compute exactly the length of this list. The elem function should compute exactly whether the element we're asking for is contained in this list. Only that if we now say that we can define such a toList function, say for our trees, right, we can call null and length and elem directly on our trees. And then you can still ask yourself, why are all these functions actually members of the type class? Why are they not just defined in terms of the toList method as separate functions? And there the reason is that while this is the conceptually right approach, right? Conceptually we extract all the elements in a list and then we compute some other function over that list. it is often not the most efficient way of doing things. Building this intermediate data structure of a list is some overhead, and often many of these other functions can, for specific data structures, be implemented in far more efficient ways than first building this intermediate data structure. And that's why they're all elements of the foldable class. But in terms of how you can think about it, it's all essentially about like, what is the order of elements? How can you extract the elements into a list? Right? And the fold R and fold L and fold L prime are also working in this sense, right? I mean, the idea is again that you can think about it as if you can extract the elements of the data structure into a list, then you can use a fold R and a fold L prime on that list. And if you look at the instances that are available, we see that, again, we have an instance for lists, and we also have an instance for maybe. And let's see what, I mean, for maybe, it's not such a terribly interesting type, but let's just see what this means, because the toList function on maybe is just going to collect the element that may be contained in the maybe structure in our one element list. If we have nothing, then we have an empty list. And then all the other things, they follow from that, right? So null is going to say, oh, true to a nothing. It is going to say false to a just. Right? The length of a maybe is going to be 0 or 1. Right? The sum of a maybe is going to be 0 for nothing, or the element that is contained in there. Right? And the product of a maybe is going to be 1 for nothing, or the number that is contained in there. Right? And so many of these functions are not terribly interesting for are not terribly interesting for the maybe type. But we could make our tree data type an instance of the foldable class as well. So because the notion of a tree is obviously ordered, right? We have a left subtree and we have a right subtree, and we could be writing a toList function on trees. Actually, that is not very difficult. We could be writing a toList function on the trees in such a way that we say, if we go from the tree of A, we can have a list of A's. And if we have a leaf with a single element, then we produce a single element list. And if we have a node of a left and a right subtree, then we do a toList of the left subtree and append it to the toList of the right subtree. Now, unfortunately, and this is for efficiency reasons, toList is not a method that is allowed as a minimal instantiation of the foldable class. In fact, we have to define fold R or fold map because these are going to be almost always more efficient base functions to define the other functions in terms of. Nevertheless, if we are not overly worried about efficiency, we can get away with defining a foldable instance for trees by using toList automatically, like our toList function in the background to define the fold R version of trees. So let's see. So using instance signatures, what I have to define now is something of this type. And I'm essentially getting these cons and nil operators inspired by what to replace the list constructor and what to replace the empty list constructor with, the cons constructor and the empty list constructor with. And then I'm getting a tree, right? And now I can apply toList on the tree to get a list. And then I can use fold R again, but now on a list. I'm passing constant nil to this. So as I said, this is not as efficient as if I would give a definition of fold R on trees directly. That would not go through lists, but it does work, and it does allow us to have a valid foldable instance for trees. And now for trees, this is a bit more interesting, right? Because now I can, for example, do let's say what were all our functions that we had available. I can check whether something is an element of a tree, right? So elem is an instance of the foldable class. So I can check whether whether 3 is an element of this tree, which has a leaf 5 here and has a leaf 3 and a leaf 4. And I forgot the parentheses. And it is contained there, right? And that is because we can now extract all the elements from the tree and then run the element function on the list, essentially, right? This is done in a similar way that what the foldable class gives us. And the null function checks whether a tree is empty. Now, actually, our trees are never empty, right? Because the smallest possible tree that we have is a leaf, and the leaf contains one element. So our null function will never actually say true. But we can compute the maximum element of a tree. Maximum, I misspelled it. And we can compute the sum of a tree, which is 5 plus 7 is 12 plus 4 is 16. And we can compute the product of a tree. All right, so 5 times 7 is 35. Times 4 is 140. Okay, so this works, and this is useful as well. Again, the foldable class also has these controversial asymmetric instances for pairs and either, and exactly the same principle applies. For the either type, only things that are injected using write are considered elements that we can extract using the toList function and that are operated over by all the other functions of the foldable class. For pairs, only the write components of the pairs are treated as elements. And this again has consequences, right? So this means that the length of a pair is, think about it for a moment, perhaps even pause the video, see whether you can predict this given what we've said so far. So I'm going to give the answer now. The length of a pair is 1, right? Because a pair always, like in this worldview, always contains one static component, that's the left component, and one element, which is the right component. The pair of an either type depends, like the length of an either type depends. If we compute the length of the left component, then it's 0, because the left component is not considered an element. But if we compute the length of a right component, then we get 1, because right is considered to tag one element. And then all the other functions, they follow from that, right? So lm3 of left tree will say false, because again, if you tag something with left, it's not considered an element. lm3 of right tree will say true. Similarly, lm3 of the pair 3, 4 will say false, because the left component of the pair is not considered an element, whereas lm3 of the pair 4, 3 is true. So these things are confusing. And again, I personally don't agree with these instances existing. I think it would be better if they were just removed. Nevertheless, they are sometimes useful, but you have to be aware how they are defined and how they work. And if you think about it, you can always remember that foldable and functor, they only operate really on data types that have one parameter. And in order to make either and pairs an instance of these classes, we pretend that they have one parameter by taking the first of their two arguments being a piece of static information and treating the second as the element position. Okay, as the final aspect that I want to discuss here is that actually both the functor and the foldable class can also be derived by Haskell, and that can be very, very useful. But that is a language extension, again, for both these classes. It's a separate language extension. So if you want to do this, you have to enable the derive functor language extension in order to be able to derive the functor class, and the derive foldable language extension to derive the foldable class. And then what we could do is, rather than deriving show here only, we could say for our tree type we want to derive show and functor and foldable. And now, of course, this is giving us errors because we have explicitly made our trees an instance of the foldable class. And I said before, you cannot have duplicate instance definitions. So we should comment out our instance of the foldable class here, and we should comment out our instance of the functor class for trees down here. And then this deriving clause is perfectly accepted, and if we try to see whether it still works, if we do fmap +1 node leave 3 leave 5, it still works now with the derived mapping method. And if we check a few of our foldable based calls on the tree type, we see that it also still works. And even if we comment it out to list as well, because to list is clashing with the foldable class as well, we can use the foldable class, the derived foldable class to list function now in order to get all the elements out of a tree. Okay, so we've seen quite a few different type classes now. There are still more type classes that are interesting to know about. There is the monoid class that just came along in the context of the foldable class. There are type classes such as applicative and monad, which are very widely used, which we'll still discuss in the rest of the course. But one other area that we have mostly excluded so far is the type classes that are being used for numbers, such as num, and there are also other ones such as an integral and fractional and some more. And I'm going to do another optional video on these numeric classes. Otherwise, apart from this discussion of the numerical hierarchy, this basically concludes what I wanted to say about overloading. It's a big topic, right? There is a lot to say, and probably there would be a lot more to say. But I think for an introduction to Haskell, we have covered the basics quite well at this point.